next, we're going to move to the 60 CKM construction by using a new approach called bidirectional wireless Gaussian splatting. And finally, we will conclude our lecture. So here's a recap on CKM. So CKM basically means a functional relationship, a functional mapping from the environment and also the spatial transmitter-receiver locations to the channel knowledge. So by using CKM, we can actually obtain the channel knowledge with a low overhead. And also by doing so, we can enable predictive resource allocation, beamforming, and also can support network deployment and optimization. So instead of different from conventional stochastic channel modeling, for example, we have various feeding channel models, right? Different from them, the CKM corresponds to a site and the environment-specific channel modeling. Okay, so in terms of channel knowledge, there may have different types of channel knowledge, and accordingly, we have different types of CKMs. For example, we can have the channel gain map, and also we can have the channel angle map or beam index map, or in the most ideal case, we can directly store the CSI, and accordingly, we can have a CSI as a CKM. Okay, so for CKM, I would like to mention two types of CKM, 3D versus 6D CKM. So this 3D CKM is widely used, and we also call it a base station to any or B2X CKM. So for the 3D CKM, basically means that one side of the transceiver, for example, the base station, whose location is given, and only the location of another side, the user equipment, is served as the input variable for the CKM model. So the B2X or 3D CKM is generally applicable for the base station-centric communication, which can enable the environment-aware communication or resource allocation between the fixed location base station to variable location UEs. So notice that for terrestrial communication, normally we can use the 2D CKM, in which the UEs are actually on the ground with the fixed altitude. And in a more general case, we can have the 60 any-to-any CKM or X2X CKM. So in this case, both 3D locations of transmitter and the receiver serve as the input variable for the CKM model, which means that the transmitter location and the receiver location can both vary as the input. So it is clear to see that the 60 CKM is more general than the 3D one that contains the 3D CKM as special cases. So we can imagine that the 60 CKM can have wider applications. For example, it can support the device-to-device communication and also can be used for network deployment. So here we give several high-level examples about the application for 60 CKM. So for example, we can use 60 CKM for predictive communication, right? So we can use 60 CKM to predict wireless channels along the moving trajectory for moving transmitter or receivers before they physically reach there. And accordingly, we can do proactive resource allocation to maximize the long-term system utility or network throughput. Another, I think, famous application for CKM, in particular 60 CKM, is for robotic communication. So nowadays, our mobile devices may have different types of robots, such as UAVs or autonomous driving vehicles. So with 60 CKM, the robots can actually control their moving trajectory to control the channel condition. For example, it can use the moving trajectory control to enhance the desirable channel condition or reduce the undesired interference channel conditions, and accordingly enhance the communication performance. So in this case, the mobility control can serve as a new design degree freedom. I think later we're going to have in the third part of this lecture, we're going to talk about the utilization of CKM. We're going to go to more details for the predictive communication. Furthermore, we can also use 60 CKM to do the network deployment. So one example is the base station deployment towards the low altitude economy, in which case we're going to use the on-ground base station to ensure the 3D coverage of UAVs in the air corridor in the sky. So in this case, the 60 CKM can enable the prediction of channel knowledge between the base station location, for which the base station actually is undeployed, and also the air corridor location that is unreached. By doing so, we can actually support the joint optimization of air corridor planning and also the base station deployment. Okay, for example, in this paper, we just consider to use the 60 CKM to help the air corridor planning and the base station deployment. So in other case, for the indoor scenario, and we can use the so-called IRS, intelligent reflecting surface, or RIS deployment to enhance the coverage for indoor scenarios. Okay, so in this case, the 60 CKM can be used to obtain the point-to-point channel knowledge between undeployed IRS location to any base station or UE locations, and accordingly support the environmental aware deployment optimization. In this case, we can actually deploy the base station without actually measure all the possible locations for the IRS, and accordingly enhance the network coverage. So we have some preliminary results in this paper. Okay, so in order to achieve these benefits, the key question, okay, or key problem at first is to construct the CKM. So let's look at the CKM construction. So in this case, first we're going to define the CKM, okay, mathematically as a functional mapping from the spatial TX and RX coordinates to the channel knowledge. For example, right, we can denote the mapping as a function M, and this is from a D-dimensional vector to a J-dimensional complex number. So here we have Q as the input. So for example, if we have a 2D or 3D CKM, then Q gonna corresponds to the coordinate of the UE. And for the 60 CKM, and we're gonna have a Q as the 6-dimensional input, which corresponds to the TX and RX coordinates. And in terms of Z, which corresponds to the channel knowledge, so we can, for example, if we consider CSI as a channel knowledge, then Z gonna corresponds to the channel vector for a MIMO for a MISO channel. And also we can use channel power gain or channel angle for Z. So notice that for this function, we can describe the function in various forms. For example, we can directly use a spatial database to represent the mapping, and also we can use an image, or we can use neural networks. And in this lecture, we're going to try to describe M by using the radiance field. So in this case, the CKM construction will correspond to finding the mapping or the function M based on the following information. So the information may contain the historical channel measurements. So if we only have the historical channel measurements, then this will correspond to a data-driven approach to construct the CKM. So we're going to train a model based on the training data from the channel measurements. And besides the channel measurements, we may also have the physical environment model. So if we can't have this one, we can have an environmental model-driven CKM construction. If we don't have this one, we may have the environmental-free CKM construction. So I think Yong and Junting have discussed different types of construction in the previous lectures. So notice that in this lecture, we're going to focus on the following scenario. So we focus on the scenario with a static wireless environment. Okay, so we suppose that the environment is given. So the historical channel measurements and the tested data, okay, are based on the same wireless environment or with fixed stochastic channel parameters. And on the other hand, we're going to make the assumption that the transmitter-receiver coordinates are perfectly known. Okay, so I believe that Junting going to talk about the case when the TX, RX coordinates are unknown in the next lecture. So in this case, we already have many types of CKM construction approaches. Okay, so for example, right, we have a retracing, in which case the actually the physical environment map is perfectly known, and we can use the software. For example, we have Wireless Insight, Siona, to construct the 60 CKM. And also, this is, I think, the most basic channel modeling approach. And also, we have single processing and interpolation-based approaches. Professor Chen has talked in the lecture 2 of this lecture series. And also, we have an image processing and a generation-based approach. So in which case, the CKM will be represented by high-resolution 2D images. Okay, so we can have a CNN-based image processing approach, and also we can have a diffusion-based generative AI approaches, as discussed by Professor Yong Zhen in the last lecture. So in particular, we're going to focus on the wireless radiance field, in which case the CKM will be represented by radiance field while neural networks or Gaussian or 3D Gaussian ellipsoids. So we have a different approach. So for example, we have the first approach called Neural RF Radiance Field, or for short, NRF2, and also we have the WRF Gaussian Splatting, okay, which is used for 3D CKM, okay, and we have recently proposed the 60 CKM approach by using the bidirectional Gaussian splatting. Okay, so we're going to talk about these approaches in detail in this lecture. So why do we need to have this wireless radiance field based approach, right? So before we talk about this, let's compare these approaches in more detail. So first, right, the first approach is for ray tracing. So basically, the ray tracing can be implemented in the following procedures. So in order to use ray tracing, first we're going to have we need to have the physical environment map. For example, in this picture, we need to know the material or dielectric property of the buildings, and also we need to know the geometric structure of these buildings in order to construct the radio map or channel map. So if we have this information, we can launch a ray along different paths or different directions by doing ray tracing. And then we combine or getting all the rays, we can accordingly synthesize the channel, okay? But this approach has the following limitations. The first limitation is that we need to have very accurate or complete environment knowledge. So you can see that in this picture, we need to abstract the buildings into some simplified structures. And on the other hand, it is generally very difficult to get the material information or the dielectric property of the environment. And the second drawback is that the computational complexity is quite high, especially when the size of the area become large. Okay, so in the second approach for interpolation or single processing based methods, so in this case we use a data set, we use a database to store the CKM. So in this case, we try to reconstruct the channel knowledge at unmeasured positions from the limited channel measurements and the reference positions by using various approaches such as KNN matrix computation or collision. But these approaches rely on the normally, okay, it only can be used for 2D or 3D CKM. So one side of the transmitter receiver is assumed to be fixed. And the other drawback is that normally it depends on the environment stationarity without accounting for the geometric structure. So you see that if the scenario become quite complicated, then the performance of the interpolation-based approach may degrade. Okay. So also we introduce image processing and generative-based methods. So the drawback of these methods is that normally it only applies for 2D or 4D CKM. Of course, we can extend to 3D or 6D scenarios by checking the images at a different altitude. Okay, but the extension is not straightforward. Basically, this is based on the 2D images. Okay, so what is wireless radiance field? So wireless radiance field is used to a kind of a 3D representation method. So you can see that the radiance field rendering, okay, is literally a 3D approach. So in this case, the radiance field is used to represent the distribution of the EM wave, which includes the light, which is for conventional optical-based 3D reconstruction, and the wireless signal, which is used for CKM reconstruction. So we can use the radiance field to denote the interactions between the EM and also the environment, including the surfaces, materials, and the surroundings. So originally, the radiance field rendering is used for 3D scene reconstruction in the optical field and for a low view synthesis. So we have the NRF and the 3D-GS, two widely used approach. So recently, people extend the radiance field rendering to the wireless domain. So we can extend the NRF to have this NRF2, and we extend the 3D Gaussian to the wireless radiance field with Gaussian splatting. Okay, and more recently, we have the 6D construction by using the bidirectional Gaussian splatting. So let's look at these approaches in more detail. So first, right, for the let's have a review about what is radiance field rendering. So for radiance field, our objective is to capture the color intensity and the directionality of the light at every point to enable the photorealistic low view synthesis. So actually, suppose that we have a camera here, and we're gonna looking at the 3D scene along a certain direction. So in this case, we denote the theta and the phi as the azimuth and the point of view angles. So the radiance field corresponds to a mapping. Okay, so we have the viewing angle, and also we're going to use x, y, z to denote the volume point location in the 3D scene. So so the radiance field are going to find a mapping, which means a function f from the volume point location and the viewing angle to the density and the RGB color at that point. So C corresponds to a 3-dimensional vector, which includes the RGB color in the optical field. So as long as we can get this kind of volume, we can get this radiance field, and accordingly we can use the volume rendering to get the color at each pixel in the optical domain. So which is obtained by computing the integration integration of the radiance along the viewing ray by taking into account the absorption and the scattering within the medium. So in this case, the expected accumulated color along a given ray can be computed by the integration. So Tn is a near point, and the Tf is a far point. Okay, so by integrating all the colors along this ray, we can get the color at the corresponding pixel. So notice that we have a T of T, which corresponds to an integration of the density to denote the transmittancy, which means the probability that nothing has been blocked along the at the ray up to that point. And also we have the color C at each point. Okay, so by doing so, we can have the color of each pixel, and if we exhaust all the directions, we can get the colors for all the pixels, and accordingly we can get the picture along this viewing direction. So in order to get this radiance field, we need to use a given measurement to train a model to get this radiance field. So how to represent the radiance field or denote the function f is an interesting problem. So actually we have two approaches. The first one is a NRF, the neural radiance field, which actually going to use a neural network or MLP to represent the function mapping f. Okay, so in this case, we're going to first use a position encoding to lift the original x, y, z, theta, phi to a higher dimension. And after that, we can use the MLP to denote a mapping from the position encoded 3D to the density and the color. So a key idea is that we're going to have the position encoding, and also we're going to have a MLP to represent the radiance field f. Okay, so as long as we get f, we can use the same volume rendering to get the corresponding image in the optical domain. So NRF can achieve quite good performance for the lower view synthesis in the optical domain. And more recently, we have another approach. It's called the 3D Gaussian splatting. And the 3D GS, okay, corresponds to so notice that, okay, for, the NRF is actually an implicit representation because a black box neural network is used to represent the radiance field, okay? But for the 3D GS, so it corresponds to an explicit representation, which can model the whole thing by a set of Gaussian ellipsoids. So in this case, each Gaussian ellipsoid will be represented by the following parameters, including the 3D position of the Gaussian, and also scanning, rotation of the Gaussian, and also use spherical harmonic parameters to denote the color along different directions. And furthermore, we're going to have an opacity of the Gaussian as alpha. By using different Gaussians, and accordingly, we can have the mapping of the final image going to be implemented by the so-called splatting process and the rendering process, which means that we're going to, in order to get the lower view synthesis, right? Suppose that we have a given view along this direction. In order to get the picture or image from the 3D thing or from the 3D Gaussians, so we're going to first use splatting to project the 3D ellipsoids onto the 2D image plane, and accordingly, we can compute the 2D position and the covariance based on the splatting process. And after splatting, we can compute the color of the pixel through the rendering process. So instead of using the volume rendering, we're going to use the so-called alpha blending by combining all the ellipsoids by using this formula. So notice that n corresponds to the set of all the Gaussians, and we combine all the parameters of the Gaussian together, and accordingly we can get the image. Okay, so based on that two approach, right, we can see that. So what's the difference between wireless and opticals, right? So actually, as long as we can represent the thing by using the radiance field, so because so wireless signal and the optics, both of them correspond to EM signals. So motivated by NRF in computer graphics, right? We can also represent the whole space by using the so-called wireless radiance field. So in this case, we can similarly use wireless radiance field to represent the environment. So in the NRF2 paper, actually they consider the case when the receiver or the base station have a fixed location, and then we try to represent the whole environment by using a neural radiance field. So they're gonna take the receiver location, PTX, the transmitter location as the input. Okay, so this is can be viewed as similar as the viewing angle of the camera, and also they have the voxel position. Okay, this is similar to the x, y, z in the radiance field in optical domain, and also they have the directional of the at the receiver side. Okay, this corresponds to the direction of the sampled ray from the Ix. We have a omega. So by given the three parameters, so we're going to use the radiance field to represent a mapping from this the parameters to the attenuation caused by the voxel, and also the scattering or the retransmit of the signal of the voxel. So we're going to view each voxel both as an obstacle which going to cause certain attenuation, and also we're going to view it as a scatter or transmitter, as a virtual transmitter, which can also transmit a signal. Okay. For example, if along this ray we have a P1 to P5, so at each point it will not only result in attenuation, but also it's gonna be viewed as a new virtual transmitter. So by doing so, right, NRF2 actually use a neural network to represent such mapping. So they're gonna use two neural networks. So one is used as a mapping from the input to the attenuation, and the second one gonna use as to predict the virtual transmitter signal. So similar to NRF, So position encoding is used for the mapping. And after we get this representation, we're gonna a new wireless radiance field rendering process is used, okay, to receive the signal at a given location. So notice that in this case, right? So they're gonna compute. So notice that delta here gonna correspond to the attenuation caused by the work zone along the ray, and S gonna correspond to the virtual transmitter or scattered signal at any given point. So this is a result from the NERF paper. So you can see that the NERF2 actually can perform much better, right, in terms of the spatial spectrum recovery. And notice that, okay, so the NERF2 paper actually considers the spatial spectrum recovery as their objective. So another wireless radiance field reconstruction method is based on 3D GS. So this is actually motivated by both NERF2 and also the 3D GS to construct the 3D CKM, in which case the receiver side is fixed. So notice that in this case, in the environment, so each Gaussian ellipsoid gonna act as both obstacle and also the virtual TX, similar to NERF2. So the main difference from NERF2 is that the attenuation caused by the ellipsoid will be represented by the Gaussian splatting, and the retransmitted signal from the ellipsoid can similarly use, okay, the MLP to represent the to predict the attenuation and also the retransmitted signal. So you can see that in order to receive the signal, right, from the radiance field, from the wireless radiance field, you're gonna use the splatting process together with WRF rendering to get the receive the signal. So although this approach performs quite well for the 3D CKM construction, but they have the several limitations. Okay, so the first limitation is that both of them actually focused on the 3D CKM construction, in which the base station location are fixed. So as we mentioned before, in many applications, especially in order to achieve the network deployment optimization, actually we need to have the 60 CKM instead of 3D ones. And the second drawback is that both approaches rely on implicit MLP-based representation. So notice that all the original 3D Gaussian in the optical domain, it is actually an implicit 3D representation approach. But in this WRF-GS, actually use the implicit, okay, NLP to represent the mapping from the parameters to the attenuation and the retransmit signal. Okay, so in this case, it corresponds to implicit representation. So it is weakly grounded by the physical propagation models. So in this case, we try to extend to the 60 CKM construction. So we're gonna have the following challenges. The first challenge is that we need to handle varying TX and RX locations. And also we need to handle the bidirectional property of the scatters or volumes in the environment, which gonna depends on both angle of departure and angle of arrival. So and also the 60 CKM contains 3D CKM as special cases. So they consider the 60 CKM also should be compatible with 3D CKM as a special case. Okay, to handle these cases, we're gonna propose the bidirectional wireless Gaussian splatting to construct the 60 CKM. So in order to look at the 60 CKM case, we actually check the literature for the optical domain in the computer graphics. So we find some interesting papers to construct the 3D scene by considering the dynamic illumination, which means that the lightning condition is actually changes. So this is similar to the 60 CKM in which transmitter and the receiver both have varying locations. Okay, so motivated by this, okay, so we try to we look at the bidirectional Gaussian splatting. Okay, So for the bidirectional Gaussian splatting in computer graphics field, okay, the basic idea is to represent the same by using Gaussian ellipsoid. But instead of considering the unidirectional scattering, because in conventional NERF or 3D-GS with fixed illumination, they only need to consider the scattering towards the camera. But if we have a dynamic illumination, we need to consider the bidirectional scattering at both the illumination side and also the camera side. So in this case, they need to use the bidirectional scattering function f to capture, okay, the varying lightning condition and the varying viewing angle. And in this case, right, they can use this one this function to represent the scattering towards different directions. Okay, so motivated by this, so motivated by the bidirectional Gaussian splatting with dynamic illumination, so we can use the same idea of bidirectional Gaussian ellipsoids to construct the 60 CKM with varying 3D transmitter and receiver locations. Okay, so what is the basic idea? So the basic idea is that we try to propose the bidirectional wireless Gaussian splatting to construct the 60 CKM in which both transmitter and receiver locations will change. So also different from the previous NERF2 or WRF-GS, in which use implicit MLP or neural networks to represent the 3D scene. So we're gonna design the bidirectional Gaussian splatting based on the physical propagation models. More specifically, we're gonna explicitly consider the distance-dependent path loss. So in this case, the Gaussian ellipsoid are used to have some physical meaning. So the Gaussian ellipsoid are gonna represent both virtual scatter clusters and also the obstacles in the environment. So furthermore, we're gonna directly use the model to construct the channel state information instead of a spatial spectrum as used for NERF2 and WRF-GS. Okay, so in order to construct the bidirectional Gaussian splatting, we're gonna extend the bidirectional scattering profile of each Gaussian by using the bidirectional spherical harmonic functions. And also we're gonna use the wireless Gaussian splatting and the wireless rendering to calculate the complex attenuation caused by the obstruction of each Gaussian ellipsoid. So as we mentioned, right, we try to have a physical propagation model inspired model. So in this case, we first look at what is the physical wireless transmission model. So here we consider the case with a SIMO channel, which means that we have a single antenna transmitter and a multi-antenna receiver. And in this case, this channel model gonna consider a single hop scatter cluster. Okay, so in this case, the channel from the transmitter to the receiver are gonna consist of both the direct path and also the scattering path. So notice that for each path, for example, direct path, right, we have a B as the steering vector for the SIMO channel, and we have a lambda as a wavelength, and the DL corresponds to the distance of the direct path, and the theta L corresponds to the complex attenuation by the obstacles during the direct path, and also we have the phase shift. For the scattering path, as we mentioned, we only consider single hop scattering. Okay, so we have a B as a steering vector, and also we have an important parameter that is the scattering coefficient, which is caused by the Gaussian ellipsoid as a virtual scatter. And also, because we are two hop, we have a DTS as the distance from the transmitter to the Gaussian, and the DRS as the receiver to the Gaussian distance. So theta is actually a complex attenuation caused by the obstructions during the transmission from the associated with the scatter, and also we have the phase shift due to the transmission distance. Okay, so you can see that this one is actually a physical model which appear in our wireless communication textbook. although we only consider the simplified single hop scattering model, right? So we can further simplify, we can further rewrite the channel model based on the angles. So suppose that we take the animus angle from 0 to pi and the inhibition angle from minus pi over 2 to pi over 2. Okay, so we can describe the summation of the S, all the passes over the distances. And also we have a direct link here. Here is the scatter link. Okay, so if we quantize the animus angle and the inhibition angle, we describe them as a set of angles, and then we can describe it as a summation. And notice that we have M as a virtual scatters, and accordingly, right? So each virtual scatter gonna result in a path at this at each angle here. Okay, so you can see that we have for each virtual scatter, it's gonna introduce a path like this. Okay, so we have B as a Steven vector, and also the gamma is the scattering caused by the virtual scatter, and also we have the theta, which gonna corresponds to the attenuation due to the abstraction by the obstacles along this passes. So DTM and the DRM actually corresponds to the attenuation caused by the free space transmission. So you can see that from this model, we take into account both the scattering effect and also the attenuation caused by abstraction, and also the free space channel propagation. Okay, by doing so, okay, so we you can see that right. So you based on this model, actually we can use Gaussian ellipsoid. So the only parameters we need to represent corresponds to the attenuation theta for each path, and also the scattering coefficient gamma for each path. Okay, so what we do is that we're gonna based on the Gaussian ellipsoid to get a formula for theta and gamma. So as long as we get the Gaussian ellipsoid model, we can use wireless splatting and rendering to fit in the complex attenuation caused by the abstractions for each pass. Okay, for example, you look at the pass from the transmitter to the scatter, right? Here is a virtual scatter. So for this pass, we can have another two Gaussian ellipsoid, which gonna cause abstraction for this pass. So in order to get the attenuation caused by the two Gaussian ellipsoid, we're gonna use wireless splatting. So in the wireless splatting, so we're gonna based on the Gaussian distribution here, so we're gonna use a parallel projection to project the 3D Gaussian to a plane, okay, in a 2D plane. So what we do is that we just use a parallel projection instead of a perspective projection used in optical field. The reason why we use parallel projection is that in our model, actually, we take into account the free space propagation. So the projection should be distance free instead of distance dependent. So by doing so, by using this projection, we can get a formula here. We can get a formula here corresponds to the 2D Gaussian parameter. And based on the 2D Gaussian parameter, we can use wireless rendering to get the attenuation. So for each path, the attenuation consists of two parts. The first part corresponds to attenuation from transmitter to Gaussian, so we denote as theta TM, and second part is the attenuation from the Gaussian, okay, to the receiver. So for each part, for example, theta TM, okay, so we just use a similar alpha blending method. Okay, we use alpha blending, and we calculate the coefficient of, for example, alpha similar to the opacity, and we have another parameter related to the phase associated with the attenuation. Okay, so by doing so, as long as we get a theta and of course the 2D Gaussian parameter G here, and accordingly we can calculate the parameter alpha and the gamma, which corresponds to the angle of the attenuation and the amplitude of the attenuation for each pass. Okay, so this is for the complex attenuation part. And the second part is for the scattering coefficient. So as we mentioned before, different from the 3D CKM part, for the 6D case, we need to have a scattering coefficient associated with both the inward angle and also the outward angle. So in this case, we're going to use a bidirectional spherical harmonic function. So in this function, it depends on, so you can see that the function depends on both the inward angle, theta m and phi m, and also the outward angle, theta prime m and phi prime m. Okay, so we just described this function as 2 parameters. So we have angle independent one and also the angle dependent one. So the reason why we decouple this is in order to facilitate the training of the parameter. So the angle dependent parameter v can further be described as a real part and the imaginary part. And for both of them, they can be fit by using a bidirectional spherical harmonic function. Okay, so the a and the y corresponds to a set of BSH parameters. Okay, so we can use this one to represent the bidirectional property, bidirectional scattering property of each Gaussian ellipsoid. Okay, so by doing so, right? So recall that we use Gaussian splatting and rendering to get the attenuation, and also we use the bidirectional spherical harmonic function parameters to represent the complex scattering coefficient. By combining them, okay, we can get the complete model for the wireless channel. For each channel, right, it can correspond to the channel vector can correspond to the summation along all the angle directions, and you can see that for each pass, right, we use the Gaussian ellipsoid to represent attenuation and scattering. And notice that for each path, we actually have the free space channel propagation. So you can see that our model actually integrate both the physical model and also the Gaussian splatting to get the final result. Okay, so in terms of training, so in order to train the model properly, okay, so we just use the spatial spectrum prediction as a one part of the training loss function, and also we use the receive the signal channel gain, as well. We use the MSE and also the MAE of the channel power gain. Use all of them. We combine the two loss function together, okay, in order to train our bidirectional wireless Gaussian splatting model. So here will be the whole pipeline for the complete model. So we have the transmitter and receiver position, right? The whole process consists of 2 parts. So we have one direct part. So we have a direct TXX rendering. This is for the direct part without the scattering. So we only use the Gaussians along the direct part as the to introduce some attenuation. And for the other parts, the virtual scattering parts, okay, so we have the parameters, including the spherical harmonics function, right, to characterize the bidirectional scattering coefficient. So we have a TX rendering, RX rendering to get the channel for each scattering path. So you can see that for the training part, right, initially we can actually use the 3D point cloud as the initial location of the 3D ellipsoid if we know the environment information. But if we do not know the environment information, we can just randomly generate the 3D ellipsoid. So then we use the wireless splatting and the wireless rendering to get the channel, and we use the spectrum, and also we use the channel gain together as a loss function. So notice that similar to the 3D Gaussian, we have this adaptive density control part to control the number of the 3D Gaussians. So we can, so if 2 Gaussians are close together, so we can combine them together, and if the one Gaussian is too large, okay, we can split them, or we can clone them to train the model properly. Okay. So before we look at the result, let's have a comparison between the bidirectional wireless Gaussian for wireless and also the bidirectional Gaussian splatting for optics. So you can see that their tasks are different. So in optical domain, they focus on 3D reconstruction, but notice that they are on the wiring illumination. But for our proposed design, right, we focus on 60 CKM construction with varying TXRX position. So for rendering, okay, so they focus on RGB colors, but we focus on complex channel vector. And for projection method, so for conventional optical domain, they focus on perspective projection in order to take into account the effect of distance. But in our case, because we explicitly model the wireless channel path loss, okay, so we consider the parallel projection. And for a number of projection plane, right? So in the optical domain, they only have one single image plane. But for our case, we have a multiple virtual projection domain at the RX. And notice that another key difference is that in optical domain, there is no phase, but in wireless domain, we need to explicitly consider the phase information in order to get the CSI. And also for the because we consider the bidirectional scattering, right, for the spherical parameters. So they consider optical scattering function, but in this case, we consider complex scattering coefficients. So in general, you can see that our method is motivated by the method from the optical domain, but you can see that there is still a lot of effort to do in order to make our method consistent with some well-established wireless channel model. So we consider in the experiment, we consider 3 scenarios. So one is conference room, and the second one is a living room, and another one is another room. Okay, so we generated the data by considering the Siona. Okay, we use the generated data by Siona for test. So notice that first, right, we compare the performance of our proposed design for 6D in order to versus some benchmark scheme for 3D. So in order to compare their performance, so we just reduce our design, okay, to the 3D scenario because as I mentioned before, the 6D case is more general than 3D. So in this case, we consider the performance matrix by using the SSIM and also the LP IPS. So we consider both NURF2 and the WRF-GS. Okay, so in conference room, bedroom, and office, for the 3 cases, we compare the performance. Okay, and this picture shows the visualization of the spatial spectrum. So you can see that our proposed design actually can predict the spatial spectrum better than other approaches. So in terms of SSIM and the LP-IPS, okay, so you can see that actually in some cases, so the WRF-GS, in some cases, it may perform better, okay? But the average performance, okay, so our proposed design, so SSIM, is slightly slightly worse than the WRF-GS. But notice that our proposed design actually works for the more general 6D case instead of 3D. But for the LP-IPS, so we can outperform them. Okay, so next we consider the 6D CKM construction, and in this case we get the training data measured on 9 distinct TX position, and we generate multiple X locations to get the training data. And for the test data, we're gonna use a different TX position, which is unseen in the training data, and we also have a multiple test at RX position, which are uniformly sampled. So in this case, there is no existing approach, so we compare it with simple MLP. Okay, so for both MAE and the normalized mean absolute error, okay, so both them we can achieve a much better performance. Okay, so in this case, you can see that our proposed design, okay, can outperform, okay, the benchmark scheme in channel power gain prediction, and also keeps a comparable performance in the 3D CKM, although is able to reconstruct the 6D CKM. Okay, so besides this performance comparison by using the data from communication measurement. So the 60 CKM construction approach has a unique benefit. That is, we can actually use the monostatic sensing data to predict the bistatic communication channels. For example, right, ISAC nowadays become more and more popular. So the devices has the monostatic sensing capabilities like radar probabilities. So if we can use a vehicle, okay, moving around a given environment, and we connect the monostatic sensing data, and if we can use this information to predict the communication environment, and accordingly we can predict the 60 CKM between any transmitter and receiver location. So this will be very important because, okay, this approach can actually avoid the need of accurate TXIX location. Okay, so we only need to know the location of the single node. Okay, so we can accurately load this node, and accordingly we can predict the whole environment information. So we do some environment experiment test. So we get the training data by using the monostatic sensing, and we use the test data with a bistatic communication channel. Okay, so this means that the training data corresponds to the signal from the same node. Okay, to transmit, and then the signal is like a radar echo signal to the receiver. And we use the test the test data is a communication channel. So in this case, okay, we compare with MLP. Actually, you can see that we can achieve quite good performance. So you can see if you compare the accuracy of the achieved performance, okay, in the monostatic case versus the previous case, you can see that if we use the similar size of the parameters, okay, if we use monostatic sensing, the accuracy will be lower. This means that in order to achieve higher the same accuracy, we need to have a more monostatic sensing data. Okay, so this is, I think, potentially is a very important application for the bidirectional wireless Gaussian splatting. So it can enable, okay, the use of the learning of a bistatic communication channel from monostatic sensing or from the radar sensing. The reason is that the Gaussian ellipsoid can actually characterize the environment, and also our model is a physical propagation model inspired. Okay, so because we can characterize the physical model, so because the sensing can actually, in some sense, right, get the environment information, and accordingly we can predict the information. This actually may not be done by using the MLP-based method. Okay, so finally, let's have a conclusion. So in this case, in this lecture, right, we talk about the 60 CKM. So we know that the 60 CKM have some unique benefits for application, right? I think that we can have a predictive communication for D2D communication, and also we have the mobility control for robotic communication, and also we can use it for network deployment, which are particularly important for low altitude economy and also the IRS. And also inspired by some techniques from the computer graphics in the optical domain, right? We propose the bidirectional wireless Gaussian splatting to construct the 60 CKM. So the key takeaway message is that instead of using some implicit representation, right, we use Gaussian ellipsoid to explicitly represent the virtual scatter cluster in the environment and also the abstraction in the environment. So in this model, we also take into account the free space path loss in the model. So in terms of results, right, the proposed design can perform quite well. And also the important takeaway is that it can enable the use of a monostatic sensing for prediction the bistatic communication channel. So this is still some preliminary results, and I believe that there are many important future directions. For example, right, so we consider CSI, and how about the channel gain map? And how about the MIMO case? And another one is how about we have the cross frequency CKM. This means that we can use the measurable data at one frequency to predict the channel at another frequency. I think our approach is doable because our approach is a physical environment based one. And another one is large scale outdoor scenario. So in the current case, you see that we use the Siona to predict the channel in a simple indoor scenario. So if we go to the outdoor, if we have a large scale, so how to reduce the complexity is still an important issue. And the last one is actually the imperfect TXRX location. Okay, so as I mentioned in the beginning, we can see the accurate TXRX location, but how to extend to the imperfect case. Okay, so it's still need some effort to do. And another one that is important is that how to use it in dynamic environment. Okay, so in the dynamic environment, we need to refine the CKM in real time. I believe that the Gaussian splatting based approach also has some advantage in this case, because in this case we only need to refine, okay, the parameter and the location of a limited number of Gaussian ellipsoids by viewing them as moving scatters in the environment. Okay, so that's all for my presentation. I will be happy to take any questions. Thank you very much.
All right. Thank you, Professor Xu, who gave a detailed tutorial on bidirectional wireless Gaussian splatting for 60 CKM construction. So we received quite a number of questions. The first question, I guess, is related to somewhere between page 26 to 28. It asked, the formula incorporates a bidirectional complex scattering coefficient. When constructing a CKM, is this coefficient treated as a time-varying parameter that adapts to environment changes? And furthermore, for irregularly shaped scatter cluster, how does this model ensure accurate characterization of scattering properties across different frequency bands?
Okay, thank you very much for the interesting question. So first, okay, so we didn't consider time varying case. So in this work, actually we consider the environment that is static. Okay, so all the scatters they may have at the fixed locations. So why we need to use this bidirectional scattering coefficient? The reason is that each cluster of scatters or virtual scatters here may have different shape. So this means that along different inward direction and outward direction, they may have different coefficient. So in this case, we need to have this bidirectional scattering coefficient. Okay, so this you can view this as a function to capture the shape or the profile of the scattering along different input and output directions. Okay, so it's a fixed environment with fixed scatters. So in the second question, you ask about the different frequency band, right? I think that is also a very interesting question. So in this work, actually, we consider the narrow band scenario. This means that both the training and the test are implemented in the same frequency band. So how to extend to the case, right? I think we have two cases. One case is that we can consider the wideband channel. So you have the training data from different frequency band. So in that case, we may need to have another parameter, for example, as a frequency band as the input of this model. So we need to fit our model, okay, as a different frequency band. For example, for the scattering function and the attenuation function, we need to have the frequency band as an explicit parameter. And another more important scenario is when we have training data in one frequency band and we try to have the channel prediction in another frequency band. So this may apply to the FDD scenario, right? So in that case, I think, yeah, we may also have the frequency in the parameter, but in that case, maybe we need to look into the detailed physical model on how the frequency will affect the scattering in order to predict the cross frequency CKM. Okay, thank you very much.
Right, thank you. So the next question. So let me just state the question. Professor, you mentioned using ellipsoids to represent scattering paths. Compared to traditional point source models, what are the specific advantages of this ellipsoid splatting in terms of reducing parameter counts?
Okay, so thank you for the question. So it is true that in the Gaussian splatting based model, actually we need to have a large number of Gaussian ellipsoids to fit the environment. Okay, so the purpose to use Gaussian splatting is not to reduce the parameter count. Instead, is to make the reconstruction as accurate as possible. Okay. So in this case, actually, each Gaussian actually plays two roles. So it's not a point source, right? I think the Gaussian plays two roles. The first role is the scattering, And the second role is that you see for each scattering path, each Gaussian gonna play the role as the obstruction. So each Gaussian along the path, okay, it's not scatter, it instead gonna introduce additional attenuation to fit the obstruction for each path. Okay, so if you use a single point source, you cannot characterize the attenuation along the path or similar like the obstruction or shadowing along each path. But if you use the Gaussian ellipsoid, right, actually you can represent the attenuation along different direction of the scattering paths. Okay, thanks.
All right, thank you. So the next question reads as follows. Thank you, Professor. I noticed that bidirectional wireless Gaussian splatting significantly outperforms NERF and wireless radiant field dash Gaussian splatting in the LP-IPS metric. Given that LP-IPS measures perceptual similarity in images, does this imply that in the CKM context, bidirectional wireless Gaussian splatting is better at capturing high-frequency fine structures of the channel in angular or spatial domains, such as sharp multipath components?
Okay, thanks. This is a very interesting question. Okay, so I think the proposed design, I think they may have this benefit. The reason is that actually we explicitly, it's like it is a explicit environmental representation approach instead of an implicit one. Okay, so as I mentioned before, so of course NERF2, right, it's an implicit one because you use neural network to represent the whole environment. And for the WRF Gaussian splatting, although it is based on the idea of Gaussian splatting, so it uses Gaussians. But notice that if you check the whole process, they mainly use MLP, right, to get the attenuation and get the scattering or retransmit signal. So maybe as our proposed design, right, maybe we model the environment in a more physical way. So maybe that's a reason we can have a better maybe performance, right, in the angular and the spatial domain. Okay, but yeah, I think there are many. This is also an interesting direction to go. Okay, thanks.
Yeah, thank you. So the next question reads as follows. Thank you, Professor. You mentioned that bidirectional wireless Gaussian splatting can use monostatic sensing data to predict bistatic communication channels, which is a breakthrough for ISAC. In practical deployment, does the accuracy of this prediction rely heavily on the specular reflection properties of the environment? For complex analog scattering paths, is the information gathered from monostatic sensing sufficient to support high-fidelity 60 CKM reconstruction?
Okay, thank you very much. I think this is a very important and interesting question. I think this not only related to the ISAC scenario by using monostatic sensing to predict the bistatic communication channel, but also related on the accuracy of the model, right? So let's go to the model here, right? So I would like to emphasize here. So although we use this model, we only consider the scatter cluster passes, okay, and in particular we consider single hop passes. But you know, in practical communication, right, in practical wireless channel, you know that there may exist the so-called reflection path. This means that you have a reflector that is smooth, and also the size of the reflector is quite larger than the wavelength, right? So that's reflection, and that so in that case, the model actually didn't take into that account. And the second limitation for this model is that we only consider single hop. But in practice, actually, I chatted with some channel modeling researchers. They told me, okay, in their real-world measurement, actually they have multi-hop scattering passes that may also account for a large portion of the energy. Okay, so but our proposed design still work. The reason is that, so here the scatters we use, or the Gaussians we use, are not the physical scatter. They are actually virtual scatters. So this means that if we increase the number of the virtual scatters, we can make our model overfit the whole wireless environment. Okay, so this means that, for example, right, if you have a reflection path in which your reflector has a quite large, so in that case, as you mentioned, the sensing signal and the communication signal may differ from each other, right? But in that case, you can view, okay, we can use a large number of Gaussians, a large number of virtual scatters to represent this reflector. By doing so, we can still make our model approximate to the reflector. So similar case, okay, similarly, we can use more Gaussians to make our model, okay, fit for the case with maybe the scenario with multiple hops instead of only one single hop. Okay, so I think this is also initial work, but how to explicitly model the reflection or multi-hop scattering into this model and train a new Gaussian splatting model, right? I think that will be an interesting direction. But there may exist a trade-off. If you consider multi-hop scattering and if you model reflection, then how to make your model scalable or make the complexity accuracy trade-off, I think that will be an issue. So I believe that there are still a lot of work to do. Okay, thank you very much.
Yeah, thank you for your response, Professor Xu. So as we are discussing on this page, maybe I also ask two questions using my privilege as a host. So one is, so we need to place a number of Gaussian balls, right, to represent the scatters. So is there any intuition on where to place those Gaussian balls to represent the scatters?
Yeah, okay, thanks, Professor. I think this is a very interesting question. So, right, so the location, because we call it a virtual scatter, and we call it explicit representation, right? It is expected that the location of the Gaussian should be somewhat similar to the location of the real physical scatters in the environment, right? So that's the reason why we use the 3D point cloud. If we have the environment information, we use this point, okay, to place the ellipsoid. Okay, so it is true that if we use this point cloud, we can significantly reduce the training time. This means that they are good initial point for training the Gaussian ellipsoids. Okay, so I think from this perspective, the 3D Gaussian ellipsoid actually, in some sense, their location, okay, is associated with the real environment scatters. But I actually asked my students maybe draw a picture, right, to show the location of all the Gaussian ellipsoid. But when we draw out the relation, okay, the direct relation with the physical environment is not so straightforward, okay. But I think intuitively they have this kind of correlation.
I see. A related question. So in the formula that you write the channel model, right? I observed that you need to take the summation over all the possible directions. So does it mean that we need to discretize the angles? And then how can we balance, I don't know, the trade-off between the complexity and the accuracy in terms of performing the discretization over the angles?
Okay, that's also a very good question. Okay, it is true that we do the discretization. So you can see that actually, in the original model, we have a number of S passes, but we actually don't know the angle of each pass. So we just rewrite this one as an integration over all the angles, right? And then we take the discretization. We use two sets to represent the discretized set of azimuth and animation angles. Okay, but in this one, I think in the experiment, when my students do the experiment, they just use 1 degree as the step size for the discretization. Okay, so I think it's an interesting problem to analyze the accuracy versus complexity trade-off by considering the value of the quantization level, right? But we didn't do that. And I think another reason is that depends on, because if the resolution also depends on the number of antenna, right? Because in this case, we only consider a 4x4 uniform planar array at the receiver side. So we have a single antenna transmitter and 16 antenna receiver. Okay, so I think in this case, for the spatial spectrum, right, we take the 1 degree as the step size will be sufficient. Okay, I think it's an interesting question. I do not have a clear answer for that yet. Thanks.
Yeah, thank you for your response, Professor Xu. All right, in the interest of time, we cannot go over all the questions. But Professor Xu will give some feedback on the ChatSpot platform. So if you have further questions, feel free to leave your comments. So here comes to the end of this lecture. Hope that this lecture further raises your interest and knowledge in CKM. Let's thank Professor Xu again and see you in the coming weeks in our subsequent lectures. See you.
Okay, thank you very much. Bye.
Bye-bye.